Hi guys, so here I have a few examples of inverse trig functions and how you solve them. Now the first thing to go over is that most books start you off with inverse trig functions that only have uppercase letters, which is important and it makes a difference. So they write it like this with an uppercase C for cosine inverse, or if they're writing it with this notation, arc cosine with an uppercase A. Those two things mean the same exact thing. They're just two different ways of writing it. Same here. See how there's an uppercase S for the sine inverse or an uppercase A for arc sine. Now, what this means is your answers for these questions are limited to only certain quadrants on the unit circle. Now, one way of remembering this is with just a little trick of writing it. Cosine and sine, they're like this. Cosine, and then shoot that off, down, like writing it down like that. Cosine and sine. What this means is that cosine can only be in quadrants 1 and 2, and sine answers can only fall in quadrants 1 and 4. This is only for the inverse problems when they're uppercase. Okay, now there's a little trick for remembering the other ones too, just like this. Cotangent, C-O-T, connects with tangent, and secant and cosecant can be written in that same clever way. So what this means is that cotangent inverse answers will only fall in quadrants 1 and 2, while the tangent inverse answers will only be in quadrants 1 and 4. And same thing here, secant inverse can only be in 1 and 2, and cosecant inverse can only be in 1 or 4. And this is only with the uppercase inverse problems. So this is, I'm going to just label this uppercase inverse trig functions. Now the other thing to note also is that when you write the answers for cosine inverse, they will be between 0 and pi. That's what we mean by quadrants 1 and 2. And the sine answers would be between negative pi over 2 and positive pi over 2. Just squeeze that in, which is quadrants 1 and 4. That's what we mean by quadrants 1 and 4. So when you write your final answers, you'll never ever be passing through the third quadrant to get to them. So if we do a few examples, I think it'll make it more clear. So for this first problem, we have uppercase cosine inverse, and that means it can only be in quadrants 1 or 2 since it's cosine inverse, but this is a negative number in here, so that forces it to be in quadrant 2. Like that. Now we know that cosine is adjacent over hypotenuse. So I label in relationship to this reference angle at the center there, at the origin, the adjacent is -1 and the hypotenuse is 2, which means that this other missing side would be rad 3, because this is coming from the 30, 60, 90 triangle. And then you should know that this angle right here across from rad 3 is 60 degrees. So our reference angle is 60 degrees, which you should also know is the same as pi over 3. And now we need to say what our final answer is. So I'm going to redraw this so it's not too crowded. So our reference angle is pi over 3, but our final answer has to be how much this is. Now when I'm working with radians, it is helpful to think of this in thirds. So like right over here, think of that as 3/3, and think of all the way around the circle as 6/3. Because that's the same thing as pi over here and 2 pi over here. So to get our answer, it's just stopping right before the 3/3 pi, so that tells us that that is 2/3 pi, because it's just short of being 3/3. So our final answer is 2 pi over 3. All right, so let's just do another example. I've got this diagram over here still that you can reference. So this problem is sine inverse of negative rad 2 over 2. So we know from our diagram over here that sine can only fall in quadrants 1 or 4, and this problem has a negative number, and sine can only be negative in 4. It wouldn't be able to be in 1. So that puts our triangle right here. Now, an easier way to deal with this number, so they would be giving you rad 2 over 2, just remember that before they rationalized this number, it would have been the same exact thing as negative 1 over rad 2. So think of it that way, and then the top is opposite and the bottom is hypotenuse, because we're working with sine. So over in our triangle here, we've got our reference angle. So opposite from that is negative 1, and hypotenuse is rad 2. And this should be reminding you that this is also 1 right there because it's a 45, 45, 90 triangle. So this is 45 degrees, which means our reference angle is 45 degrees, but then you should also know that that's the same thing as pi over 4. All right, so to get the final answer, I'm just going to redraw a clean picture. This is our answer. We need to go straight to it because pi over 4 is just the reference angle. So to get to there, we would say negative pi over 4, because you're just going in the negative direction straight down from 0. So the final answer for this one is negative pi over 4. Now this third question is just a two-step problem, but it's very similar to the ones that we've already done. What you need to know is that you start from the inside, so you work your way from the inside out. So the first problem I'm going to concentrate on is tangent inverse of negative 5/12. Now I know from our reference diagram over here, here's where tangent is located. Tangent inverse can only be in quadrants 1 or 4. Now since they gave us a negative number, it'll have to be in 4, like this. Then you should remember that tangent is opposite over adjacent. So opposite from our reference angle, we would have negative 5. Adjacent would be 12. Now we will need to figure out the hypotenuse to be able to answer the second part of the question, which is doing cosine. So you could use the Pythagorean theorem. You could say 12 squared plus negative 5 squared equals c squared. So 144 plus 25 equals c squared. That's 169 equals c squared. So take the square root. So 13 is equal to c. So this right here will be 13. So now we don't have to actually find the angle in this one because ultimately they wanted us to find the cosine. So what we can do is just use the triangle, and I'll just write that down. Use the triangle and the fact that cosine is adjacent over hypotenuse. So the final answer, adjacent is the 12, and hypotenuse is what we just solved for, which is 13. So the final answer to that question is just 12/13. And one final example that I wanted to do is this one, sine inverse of 1. So when you have a 1, a 0, or a negative 1 in the parentheses, it will usually be quadrantal, which means it's not going to be the type where you draw the triangle. So if we think this through, what you'd have to think of instead is that think of the fact that sine is the y-coordinate on the unit circle. So if you think of the circle as a whole, quadrantal means it's at one of these 4 places, which are just ordered pairs. They wouldn't be triangles. So that point is 1, 0, this is 0, 1, this is -1, 0, and this is 0, -1. So the fact that we're trying to solve sine inverse of +1, and the fact that we know that sine is the y-coordinate, the only place where that's happening on the unit circle is right here. That's a y-coordinate of 1. So the answer to this problem is this angle up here, which we know is pi over 2. So this answer is pi over 2. So anytime you see a 1, 0, or -1 in the parentheses, start thinking of quadrantal instead, and you can just immediately draw this picture with the circle and label the 4 points and look at it that way. The only exception to what I just said to you is if it's tangent inverse of 1, because since tangent is opposite over adjacent, that would be the triangle. It is a triangle where the opposite is 1 and the adjacent is 1, which is a legitimate triangle. It's the 45, 45, 90 triangle. So we would know that that angle is 45, and so the final answer would be pi over 4. So that's an exception to when you're looking out for a 1 or a -1. But if there's a 0 in there, it would definitely be the quadrantal kind. So just remember that tangent inverse with a 1 or with a -1 is an exception to what I wrote up here. And that should cover most of your examples that you'll come across with these inverse trig functions.